Good afternoon, everyone, and welcome at the last press conference of this year's General Assembly. It promises to be very interesting, as we have a bunch of renowned scientists who are all experts on volcanology and its relation to mass extinctions. This press conference includes two presentations. The first one will be given by Henrik Svensson and Linda Elkins-Tanton. Henrik Svensson is from the Physics of Geological Processes Department of the University of Oslo, and Linda Elkins-Tanton is of the MIT in Cambridge. The next group will consist of Vincent Courtillot, Thierry Adatte, and Gerta Keller. Vincent Courtillot is of the Institut der Physique du Globe from Paris, France. Thierry Adatte is from the Institut de Géologie et Paléontologie of Lausanne, Switzerland. And Gerta Keller, right here next to me, is of the Department of Geosciences of the Princeton University. We will start with the presentation with Henrik Svensson and Linda. Please go ahead.
I'm sorry, I need you to show me how to make it full screen. Is it this? I am a Mac person.
Yeah, so am I.
So we go back to the beginning.
I can't help.
Fantastic. All right, thank you. So this presentation is based on work that's going to be presented tomorrow at the Large Igneous Provinces and Mass Extinctions session, but it's very closely related to the other group as well. I think it makes a nice united story. And so, of course, volcanoes are very topical at the moment. Everyone is paying attention to Iceland. And so what we're trying to do is look in the historical record and try to understand better what large volcanic eruptions might do to life on Earth and what the connections are between the interior, the solid Earth, and the atmosphere and the biosphere. And so just as a point of comparison to have us understand where we are, these are the volumes of volcanic products of a number of different volcanic eruptions in the past. And if you would look at the very, very tiny end, there is Mount St. Helens, which was big news to a lot of us, only a cubic kilometer. And Iceland, the Laki eruption, extremely topical for us now, about 12 cubic kilometers. And this is a very important point of comparison because the Laki eruption was indeed volcanic lava flows. And that's really what we're talking about today is volcanic lava flows, but on quite a different scale. Most of the rest of the boxes here would be more explosive eruptions. And what we're talking about are large igneous provinces that produce lava on a much greater scale than what we've seen in the past. And the example that we're going to be talking about particularly for part of this session, and then we'll be looking through history, would be the Siberian flood basalts, which happened 252 million years ago, much longer ago than Laki. But this is the volume comparison. You can see the small boxes from the previous slide and then the Siberian flood basalts. And these were indeed lava flows, but on a far greater scale than what's been seen in the past. And then it's been shown primarily by Courtillot here to my right, that there is an amazing coincidence through geological historical time between global extinction events and the eruption of these large igneous provinces. And you can see here with the ages of the mass extinctions on the vertical axis and the ages of the large igneous provinces or the flood basalts on the horizontal axis, that there is a one-to-one relationship between a number of the very largest extinctions and some of these large igneous provinces. And so this is what we're working on. We're trying to understand the links between these volcanic eruptions and the extinctions. So the new results in particular that we wanted to highlight, we've put into three categories. Of 55 million years ago, there's new age evidence that there's a very close relationship between volcanic intrusions and an attendant methane gas release offshore of Norway, which triggered a global warming event, another topical thing here, the Paleocene-Eocene thermal maximum, and this is in particular Henrik Svensson's group's work. 252 million years ago, this is the Siberian flood basalts, which a number of us here are working on. New data from China is reinforcing the connections between the flood basalts, gas eruptions from the flood basalts, and carbonate rocks laid down in the oceans and ocean acidification. And ocean acidification is, again, a topical thing for us today. Our oceans are being acidified as well. And then finally, 510 million years ago, a large igneous province that's received relatively little attention because it's so old, new ages now link that very closely with another mass extinction. So we have additional evidence for the connections between large igneous provinces and mass extinctions. And so what is the link? And if you look at those volume comparisons, and you know that when Laki Turkey erupted in 1783, people died in Great Britain from the fluorine gases that came from Iceland. It would seem obvious that this would be the link. However, it's been contested for many years that these flood basalts could cause global extinction events because they're not thought to produce a lot of toxic gases or greenhouse gases or things that would create a global environmental disaster. And yet we're finding increasing evidence that this is the case. And the key seems to be the crustal rocks that the magmas come into contain within them elements that can become greenhouse gases and can become toxic gases in the atmosphere. And the magmas mobilize those gases from the rocks that they come into, and those go into the atmosphere. And so this is the particular link we're looking at: the magma, the crustal rocks, global environmental change caused by atmospheric chemistry, and extinction. Here's a photo from our fieldwork in 2008 in the Maimiecha River at about 72 degrees north in Siberia. The brown rocks on the left are solidified magma, and the black rocks on the right are coal. And so in this case, there was a coal and magma interaction, and those magmas on the left, the brown ones, contain 5 weight percent of carbon. It's an unconscionable amount of carbon for a magma to carry, and this would be degassed as CO2. In another place, these are Ordovician gypsum-bearing sediments that the magmas also interacted with, and what they would get there would be sulfur, another very quite toxic and damaging gas for the atmosphere. And so now I'm just going to hand it over to Henrik, and he will give you a little more details about these 3 featured results, and that'll be the end of our part of the presentation.
Thank you, Lindy. I will present briefly the main results that will be presented at this EGU meeting. So the first topic is the relationship between the Northeast Atlantic volcanism and the Palestinian thermal maximum that occurred roughly 55 million years ago. So the last 6-7 years, we've been working with the hypothesis saying that the global warming, the PETM global warming, was triggered by gas eruptions from offshore Norway. And the main mechanism is heating of sedimentary rocks containing organic carbon by volcanic intrusions, thereby triggering eruptions. We have field data, as you see on this map, showing that, and seismic data showing that there indeed is a lot of huge eruption craters located exactly at the Palestinian paleo seafloor. The main challenge so far has been to date precisely the timing of the crater formation and compare that with the timing of the climate perturbation. So to be able to prove that these 2 events are linked, the volcanism and the climate event, we need to also prove that they occurred at the same time. But so far, we haven't been able to actually date these sill intrusions, these volcanic intrusions, because they're hard to get at. We need boreholes from the oil industry. And we have been lucky, we actually managed to get some good data, and we discovered this mineral zircon in these sills, which can be dated quite precisely. So if you look at the section on the right-hand side, we see kind of this log through parts of this basin, and in red we see the sill intrusions. So we managed to get zircons from this zone and also from that volcanic layer. And when we dated these rocks, we got ages of 55.6 and also 56.2 million years ago. So this upper age is quite robust. This lower is a bit more sketchy. We only got like 40 or 50 grams of sample material to work with. So it's quite a hard job to do. But this upper age can we then compare with the age of the Palestinian thermal maximum. This is the age of the Palestinian thermal maximum, which you see here. And the problem is that the boundary is not dated precisely. It's based on dating of volcanic rocks, and then they use cyclostratigraphy, which is then to look at the patterns in the rock sequences to kind of recalculate the age of this sequence. But if you see our age, the zircon age, fits reasonably well with the age of the assumed age of this climate perturbation. So in conclusion, we say that this is strengthening the link between the volcanism and the PETM. Okay, the second result is going further back in time to the end Permian extinction, and this is work by Jonathan Payne from the US. And what they've done in South China is to look at carbonate rocks that spans this mass extinction. And they have in particular measured the isotopes of carbon, and they have measured the isotopes of calcium, which is a sort of unusual element to do isotopes on. And their main conclusion from this study, I have to be brief here. You can yourself ask questions to Payne tomorrow at the session we are arranging. The conclusion is that they believe these data can be best explained by CO2-driven ocean acidification, because these rocks were deposited in the ocean. So they see evidence for CO2 into the atmosphere triggered these changes in the ocean, also affecting both the carbon cycle and also the calcium isotopes then from the ocean water. And as a conclusion, they said that this points towards submarine traps, volcanism, and degassing of CO2 as a trigger for the mass extinction. The third and then the final result that we would like to present here is on the so-called Kalkarinji large igneous province, or the so-called forgotten large igneous province. And this is work by Fred Chaudin, also in the audience. You can ask questions later. So this is actually a really big volcanic province in North Australia and Central Australia. Covers more than perhaps 2 million square kilometers, and on the left-hand side you see some of the examples of these lava flows. So part of the business of linking volcanic provinces to climate perturbation, I mean, the first order question is to get good ages on the volcanism, and then compare that with the ages of the climate perturbation, of the extinction. So in short, Chaudin and colleagues, they have dated the lava flows in Australia to roughly 510 million years ago. I mean, if you look at this diagram here on the left, it shows extinctions or number of families plotted here on the x-axis. So here is this extinction in the Cambrian that they would like to address with these new ages. So they can compare the ages of the volcanic rocks with what is believed to be the age of the extinction, and that's also roughly 510 million years. So again, as a conclusion, it appears that the lava eruptions of this large igneous province occurred at the same time as the extinction in the Cambrian. Final slide. We'd like to invite all of you to the session we have on Friday. It starts at 1:30 with posters from 9 in the morning. So any questions you might have, you can ask us later. We have some handouts about the slide is a handout, and also some more handouts for you to, if you're interested in this topic. Thank you.
Since you're the expert, can you get us?
Oh, yes.
So who's next? You, Gerta?
It's you.
I am? Okay.
So you have to just escape.
Right, I think I'm here. And then full screen.
Brilliant.
Thank you very much. As you can see, the debate is not on whether extinctions were due to large igneous provinces, but whether you're a Mac or a PC user. That really divides the world into two categories. Right. Actually, the two meetings we are representing should most likely, from an organizational point of view, have been merged. And it's very good that we are able to address you together, because we really are approaching a big geological problem, which is these huge pieces of lava. There are about a few tens of them. And even I could remove the S. I mean, there's probably less than 20 in the last 500 million years. So they are fairly rare objects. They're huge. They're all on the order of 1 million cubic kilometers. So being French, I always use France as a comparison. That's France covered by a couple of kilometers of lava. So you can scale it to your country or wherever you want. That's an enormous amount of lava. And this has consequences for mantle convection, geodynamics, petrology, paleontology, extinction. So we are focusing on extinctions and large igneous provinces because that's what gets most people, including us, very excited. But it has major consequences on how the Earth functions, how the layers of the Earth are coupled, whether what creates these large igneous provinces comes from all the way down in the mantle, maybe at the core mantle boundary, 2,900 kilometers below this room. And these are still very hot and actively debated topics. I have a little bit selfishly focused in this short presentation on the work that our group has been doing, but many other groups, some represented at this meeting, have joined it. We started with one particular large igneous province, and you will find the same words, and I know we all hate jargon, but you will hear large igneous province. You may hear the word trap, T-R-A-P, which is an old, actually I was told Dutch word from 17th, 18th century geographers. When they first came to India, they saw what you're seeing in the upper right corner, piles of lava flows over thousands, hundreds of thousands of square kilometers, these flows being sometimes tens of meters thick, and you could follow these flows for large distances, and when they erode, they look like a staircase. And trap, apparently, I'm not a linguist, is a word, Treppen in German, I think, which means staircase or stairs in northern languages. So this is the body that many of us concentrated in as the topical large igneous province, before going to the other ones, which very rightfully have been quoted. what we found, several groups, approximately 25 years ago, and I have to come back to this, was rather simple. When we studied the stratigraphy of that lava pile, a few thousand meters of lava at that time, we found that there were only 2 magnetic reversals recorded in the lava pile at a time when we knew the Earth's magnetic field was reversing rather fast. So that placed the very first constraint that it had to be brief. Then we used some of the techniques that have been mentioned, absolute dating using isotopes. At that time, we were mostly using potassium-argon and argon-argon, showed that the age of the Deccan was around 65 million, very close to the time of the Cretaceous tertiary mass extinction, which got everyone excited. And then the paleontologists joined it by finding fossils in sediments which were either just under the lava or interlayered between the lava flows. And all of these together, as we understood them 25 years ago, were the first shock. These millions of cubic kilometers of lava had been erupted at approximately the time of a mass extinction, and the most famous one, because that's the one when dinosaurs disappeared, and the thing took 1 million years. At that time, 1 million years was incredibly short, but it was also the kind of precision that we could get with our techniques. So we have felt after a few decades that we had to go a little bit further, and what several groups have been doing now over the last, I would say, 5 years on various large igneous provinces. We have done it on the Deccan, and we're now doing it on the Karoo in South Africa, is very carefully measure the magnetic direction of each flow. When these directions are almost identical, it means the time between 2 flows has not been long enough to record the changes of the magnetic field, which we know from present-day measurements. We call that secular variation. And we've been able to place constraints on the timing of those lava flows that display the same magnetic directions. And in this picture, you're basically seeing on the left the cliff of the Deccan lava over 1,000 meters in Mahabaleshwar in India, and the little colored lines you see here in orange are all lava flows that, to your right on this particular projection, are giving the same magnetic direction. Hence, we believe the 180 meters of lava was erupted in less than 100 years, and if actually secular variation went at that time at the same speed it does today, it could even be less than 10 years. So we're discovering that enormous amounts of lava were produced in remarkably short amounts of time. Moreover, and this has been in particular the work of my 2 colleagues to my right, Gerta, Keller, Thierry, Adatte, and their colleagues, but also a group of volcanologists with Steve Self, Mike Widdowson, and other colleagues. They have located an outlier, a piece of lava that has been spared by erosion in India, because actually the original extent of the lava was far larger than what remains today, probably twice as much, plus what has been rifted away when the Arabian Sea opened, the rest being now found in the Seychelles Islands, where actually rocks have been drilled and found which are the complement of the missing part of the flood basalt. But what's interesting is these Raj Mahal traps have been fairly clearly linked to a source which is where, at the other red end of my line, almost 1,000 kilometers away. If you take together the thickness, the length over which you can recognize a given flow, and the amount of time that that flow took to erupt, you find that it's really mind-boggling. Some individual lava flows were probably as large as 10,000 cubic kilometers. I'm sorry that we can't quickly jump to what Linda showed you, but when you saw her blue and red cubes, remember the Laki eruption was 15 cubic kilometers in approximately 1 year. Now, we are talking about flows that were 10,000 cubic kilometers in about 10 years, 100 times more per unit time than the Laki, for 10 to 100 times longer. And that's one flow. And there are tens of flows in the Deccan. So you start understanding that the volcanism at the time of these large igneous provinces is characterized by pulses. And the size and speed of these pulses is orders of magnitude larger and faster than what we realized 25 years ago. And we can calculate how much carbon dioxide, sulfur dioxide was released. And we have less and less doubts. You heard Henrik talking about methane. You saw these Ordovician rocks in the Sabian traps being able to release sulfur or carbon and digest and go as SO2 or CO2 into the atmosphere. So I think we are around this table, we're all thinking that we really have the trigger of what has done so much harm to the biosphere at these times. And I'm sure you remember that this whole idea has been the focus of controversy with the 1980 excellent and important idea that it might be an impact in Mexico, in Chicxulub, that generated the extinction. There are still to this day differing views, which you will hear, about the exact timing and meaning of cratering, how many craters, how many impacts. But what we can show on our side is that the amount of of gases released by the impact is on the same order as the amount of gases released by one Deccan megapulse. So the very important new finding, contrary to what we thought 25 years ago, we thought, well, these things are taking place in 1 million years. So if you divide the amount of stuff they released in the atmosphere by 1 million years, you don't get large fluxes. But if there were a few short pulses, decades to a century long, then the pulses become large as the Chicxulub impact crater. And so the view in my group is that there was an impact at the KT boundary. There was no impact at any other boundary demonstrated. So the general rule of mass extinctions is LIPS, mass extinctions, flood basalts. We're actually only missing one. We're missing in the whole Phanerozoic in the last 500 million years. Now that the Cambrian one is apparently found, we are working on the Devonian one, which we are not even ready to show it at this conference. There's only one missing, which is the Ordovician. But I think we really found the rule rather than the exception, and the impact was there, but the impact most unlikely could not have been the single cause or even the major cause of the mass extinction.
Okay, so we can just...
Okay, celui-là?
I guess.
And full
no,
screen?
this is the other one, sorry.
I'm sorry.
Yeah,
then we go to this one.
Yeah, okay.
And the full screen is this guy. Okay.
Okay, thank you very much. In fact, we are just going on with looking for a lot of evidence that Deccan traps first was preceding very closely the KT boundary extinction, and we try to use a lot of different proxies. And you have a list here, and I don't want to talk about all these things, but all these proxies are really indicating that, in fact, the main body of the Deccan trap erupted very close from the KT boundary, and this is the main message that I want to tell here. And I will just take one example here. It's a recent paper presenting a very high resolution of osmium isotopes. And in order to make it simple, when you have a negative excursion in osmium isotopes, it means either that you have huge volcanic activity, like the Deccan traps, for example, or an impact. And what you can see here at the end of the Cretaceous, that megapulse, that to say 80% of the total pile of the lava flow from the Deccan erupted very close to the KT boundary, as indicated by these osmium isotopes. When I say very close, it's a question of perhaps 200,000 years, perhaps less, perhaps coinciding with the KT boundary. And moreover, you can also see that we have some switch a little bit below that, which may correspond to the Chicxulub impact. As you know, we believe that Chicxulub impact predates slightly the KT boundary, and clearly the maximum of the excursion may correspond to the KT impact by itself, marked by the well-known iridium anomaly. Okay. And we have other proxies. I don't want to go in more details, but here, for example, strontium isotopes also are very nicely indicating that we have change in climate alteration due to this large eruption slightly before KT boundary. Again, this may also indicate acid rain, for example, increasing alteration. When you have increasing of the strontium ratio, it means that you have increasing alteration, and it just means that you have a lot of acid rain in order to do that. And clearly Gerta will talk a little bit more about the biotic effect, but here I think, a lot of extinction pattern doesn't really coincide with the KT boundary by itself, with the iridium anomaly. What we know that extinction began quite well before KT boundary. It's mainly linked to sea level fluctuation, climatic fluctuation. whether really an acceleration close to the end of the KT boundary, and this is very clear with the reddest and extinct group. We got extinct slightly before KT boundary. It's clearly also the case of a decline in diversity of dinosaurs slightly before the KT boundary, and you can see the same with the plants and so on. And it indicates that something really big happened somewhere 100,000 years before the KT boundary. So we have more and more indication that Deccan traps probably was one, if not the principal causes for this mass extinction. And here on that slide, you can also see that Gerta will talk more in details on that. But we think also that we have a multi-impact story. And I think if you had Deccan traps activity, impact, sea level fluctuation, climatic fluctuation, you have really all what is necessary to have a very nice KTB extinction. Thank you. Yeah.
Expert now.
Okay, we are coming to the end. So basically what I will talk is what is really the kill effect of volcanism, and for that matter, the Chicxulub impact. So I will start with Deccan volcanism. And this illustrates quite well what I believe is probably going to be very soon the body of the evidence will show that the dinosaurs essentially suffered from Deccan volcanism. What I want to look at, we have two major catastrophes. One is one mass extinction. One is, of course, the Chicxulub impact. One is Deccan volcanism. And in some ways, I'm going to show you that the two, not so necessarily that the two are connected, but that there are biotic effects that we can trace all the way from India into Texas. So, we already, Courtillot already talked about the three megaphases, but briefly it is, the first pulse is actually at 67.5 million years. Then there is a long period of nothing. The megapulse is just before the KT boundary. And when I talk about the mega, we really are looking at these longest lava flows in Earth's history, the ones that flowed clear across India, 1,500 kilometers and out into the Bay of Bengal. And this is where we focus on. They are virtually at the end of the Cretaceous. And then there is another one. There is a period of quiet, volcanic quiet for about 280,000, 300,000 years. After that, and then there is the last pulse, and that's in beginning Chron 29. I will talk about each of these and the biotic effects. Here, what you're seeing is the first pulse at the bottom. And the way we assess this, there is a planktic foram. These are single-celled organisms that lived in the ocean, made their shells out of calcium carbonate. They suffered virtually complete extinction, except for some survivors for a short time. And the little guy there, it's a Gymbolithria. This one has survived to the present. In fact, it has always been present. It blooms like algae blooms when disaster conditions occur, and nothing else survives. This one will thrive, and it's sort of our yellow canary in some ways. So what we've looked at is at these blooms, and the blooms at the KT boundary, where this guy in the post-mass extinction phase is nearly 100% of the marine fauna. We see that in the middle one there, the red marks the KT boundary. As you can see, it starts below. It is coincident with the onset of these mega pulse of Deccan volcanism. It also coincides with climate warming, followed by climate cooling, then by the mass extinction. And then the last pulse is this last Deccan phase in the early Daunian, and we just discovered that we also can recognize this pulse as a crisis event in particularly through the Mediterranean, from Israel, Egypt, Tunisia into Texas. So we can actually identify biotic effects of each one. The first one, the smallest pulse, still had global effects, but and we can trace it into Texas. It's recognized, of course, also in India. The second pulse is the one that caused the mass extinction. After that, we have a delayed recovery. There is only crisis fauna that survived. And then the last pulse, and only after the last pulse, did marine conditions and the ecosystem return to finally to normal. Another biotic effect is for the specialized guys that really went extinct right at the boundary, and essentially none of these survived. But in the stress conditions prior to their extinction, particularly coinciding with the warming phase, which is global in nature, and even in deeper marine water warmed by 4 degrees Celsius, the stress response is dwarfing. And I mean, the species you can see there on this graph below is the normal size relative, and in the red is the dwarfed size. They dwarf by at least 20%. Why do they do this? Well, they're trying to mature sexually faster so they can reproduce faster so that some will survive. And it didn't help them because they were way too specialized in their food sources. Now, why do we believe that Deccan volcanism is the more likely cause for a mass extinction than the Chicxulub impact? Well, recently there was a science paper by Schulte et al. It was, I think, March 5, that Schulte et al. And 40 co-authors that claimed that all is as predicted in 1980 by the Alvarez theory. Chicxulub caused a mass extinction, and that's it. And volcanism had nothing to do with it. Well, I'm not directly going to talk about this, but I just want to alert if you want to look into that. If you look at Geosciences online as of yesterday, there is an article there on the KT mass extinction theories and controversies, and it gives you some history of it. And so it was posted yesterday. Now, but here is just one slide that shows you why we believe that Chicxulub cannot be the KT boundary, the cause for the KT boundary, because it isn't of KT boundary age. Now, this is a mountainside of El Peñón in northeastern Mexico. The upper line is the base of a sandstone complex, which is popularly called a tsunami, or interpreted a tsunami event. And it's not a tsunami, impact-generated tsunami. It is not, because it has a lot of bioturbation. Plus, at the base of it, they are channel infilled. At the base of it, there are 2 spherular layers separated by a limestone. And obviously, all this cannot be deposited within a few hours to days. It takes tens of thousands of years. And we believe that's related to a sea level low stand, erosion from shallow areas, and downslope washing and infilling deep marine channels, which this one was at 500 meters depth. Now, what we looked for is if those are not those are reworked, not the original fallout, then the original one should be older. And so a number of Princeton students were digging a trench at the back of this mountain, and lo and behold, 5 meters down, we discovered the actual primary fallout. It is 2 meters deep, thick in just spherules, basically, in the center of this channel fill, and then it thins out, but you can trace it over 100 meters in outcrops. And after that, it tips below surface, so we no longer have the outcrop to trace. It has no rework material, no shallow water material. It is essentially settling of spherules directly onto the ocean floor. Now, so that is the reason. Now, when we look at across this primary impact spherule layer, what biotic effect it had on the fossils, you see in the lower slide, the bottom green is the original or the primary layer. And you can see that every species, even relative abundances, they are present below and above, and there isn't much of a difference. Even whether you look at stable isotopes or in any way, we cannot see a major significant environmental effect and not a single species extinct. In contrast, if you go up to the KT boundary, and that's the upper half of this, you see that the mass extinction is very clear. And it is at an interval with iridium anomaly and delta C13 shift, and absolutely no indication of Chicxulub impact spherules. So that is the reason, and this is the same slide. So just to summarize, we have Chicxulub impact predates the boundary. By the old time scale, it was 300,000 years. By the new time scale, scaled is 160,000 years before the KT boundary. We've got, of course, the Deccan main phase of eruption, which we don't know yet whether it spans how many thousands of years or 10,000s of years before the KT. Then we have the mass extinction. Now, I do believe that there is another impact at the KT. As we indicate here with a question mark, we don't know of any crater. Some have suggested that it might be in India, but I doubt that. The reason we believe it is because there is a large iridium anomaly at the KT mass extinction. And we also have it in India, in a place in the northeast, in a place called Meghalaya. And it is about 12 parts per billion. And looking at the geochemistry, it has both volcanic and extraterrestrial source to it. So we believe that there must be an impact in order to provide that iridium anomaly, and that can also be seen worldwide. But Chicxulub, it is not. And I think that's where, yes, and then the last Deccan phase, of course. There is also a small iridium anomaly, incidentally, and Deccan eruptions, most major ones, we can find some minor iridium. In other words, there is iridium also from Deccan eruptions. We do have one in about the time of that. We found it now in everywhere through the Caribbean, where we looked, and the South Atlantic. And that's where I will end. Thank you.
Thank you. Thank you, everyone, for your very interesting presentations. There's time for the press now to ask questions.
Holger Kroker, freelance from Germany. If you say that these volcanic eruptions are triggered the mass extinctions, do you have any idea what triggered the volcanic eruptions?
Well, it depends how far and deep you want to go. There's triggers. Clearly, the mass of lava which is produced, which is on the order of millions of cubic kilometers, requires melting an enormous mass of mantle rocks. If very roughly I assume that the melt is 10% of the original volume that had to be melted, you're going to 10 or more million cubic kilometers that have to be melted. If you place that volume in a sphere, you redo your 4/3 of pi r cube from way back when, you will find that that sphere occupies the entire upper mantle. There is an ongoing debate as to the depth of origin of these massive instabilities, which we call plume heads. Some people think they might come from 400 to 600 kilometers deep at the transition zone between the upper and lower mantle. I'm among the people who think that in order to produce such, and I think that most of us are probably of that idea, in order to produce such a large head, if you remember a lava lump, that's just like your red fluid in a yellow lava lump coming as a blob on top and then with a thin tail behind. In order to form the head, you need to have time and space. And the idea is that actually all of this could come from the core mantle boundary. So the base of the mantle, 2,900 kilometers deep, so I was saying under this room, there is a layer about 100 kilometers thick, which because of old seismological jargon is called D double prime. I mean, the other letters have been lost since the 1930s or 40s, but that D double prime has remained and is the focus of interest of many Earth scientists beyond our two talks. There are several actually going on. There's a lower mantle session right now, which we're missing, which discusses problems related to the lower mantle. Now, these instabilities, why? Well, they're trying to get rid of the Earth's heat. The Earth is trying to get cold. It's trying to lose its original heat from 4.5 billion years ago. It's doing so mainly by mantle convection and plate tectonics. But apparently sometimes that is not efficient enough. And from time to time, maybe every 30 million years, but that's very irregular, a blob comes from the core mantle boundary to get rid of more heat. So it's another alternate mode of convection in the mantle. Once the head has produced the plume and the extinction and everything we told you, the plates continue to move above not the head, which is gone, but the tail. And the tail is very thin, and it produces hotspots. And Iceland, Reunion, Hawaii, several other islands are the present-day remnant tail of what used to be a head. And if you trace the volcanoes under the oceans from these current hotspots to way back when, in many cases you end up with a flood basalt.
If I might just add briefly to that, there is a huge debate in the scientific community about can we actually observe these plumes happening. They're a natural theoretical consequence of cooling the Earth, that you would have hot but solid material rising up through the mantle to bring its heat to the surface. And so there are a number of ways that people are trying to actually see them through seismic waves. For example, it's very controversial. People can trace the hot material down to a certain distance but not so far, and is it that it stops or that we can't see it? Not known. But we also look at the rocks themselves to try to determine the temperatures. And we have evidence in Siberia now that some of those magmas erupted at as much as 1600 or 1650 degrees Celsius, which is much, much hotter than what you find under a mid-ocean ridge. So it's quite apparently a different mode for the interior of the Earth.
Maybe there should be one other thing mentioned. Frequently in media articles, in popular articles, it is said that the Chicxulub impact could have triggered Deccan volcanism. And I have received hundreds of emails from people. In fact, it's probably filling a book by now. Of laymen who were telling me all the methods that it could trigger it by anywhere from stomping on a tube of ketchup, which would squirt out from the pressure on the other side, to what other things. The point is here that, number one, Deccan volcanism started at least 2 million years before with the first phase of eruptions. Secondly, while we now place the Chicxulub impact within the main phase of Deccan eruptions, the models that are being done actually by some at Princeton right now to test whether this is possible show, number one, that Chicxulub and Deccan were not antipodal at the time. Number two, that it's physically impossible to trigger a major volcanic eruption at the other side of the globe. So.
Okay, please, questions first. If you have no questions, I just wanted to add something. We are all researchers and teachers, and there's something I found that we have to convey our students, which I would like to convey to you as you maybe conveyed to your readers. I found that very often, because of the attraction of everyone to dinosaurs, people focus on the Cretaceous tertiary extinction. And I mean, some of us clearly like that. We've spent years working on that. I think from a science point of view, it's actually more important now to realize that what we are seeking is not only a detailed understanding of what happened at the KT boundary, but we're trying to understand a general mode of functioning of the Earth. As Linda and I said, these plume heads are something which is essential to Earth geodynamics. They are the missing part which was not in plate tectonics. There's basically plate tectonics unchanged after 30 years or 40 years, plus plumes, which actually one of the fathers of is Jason Morgan, who's actually attending this conference coming from Princeton, and not now in Harvard, I understand. So we really have something that is very fundamental. And the idea I think we'd like to convey is wherever these things come from, they're a major geodynamic operator of the Earth's function. And the second one is we're looking for general rules. Many people say, well, why should two extinctions be alike? It could be a sea level rise this time, an impact this time, a flood basalt this time. It could, but that's not how I think science works. Science works by trying to find the simplest model, the famous Occam razor idea, that fits observations, until some observations force us to abandon the model. I believe that what has changed in 20 years is that even though, as you hear, we're not disclaiming the impact, contrary to what many people say who try to oppose us, we are saying that regardless of the details of the KT boundary, the general process by which mass extinctions occur on Earth is flood basalt volcanism. And as I was telling, and as we showed on two pictures, we now have found the mass extinction large igneous province relation for almost all but one missing, which is the end Ordovician mass extinction, for which we've not yet found the culprit. But for all the other ones we have. And the next step is these huge things, they are not generating the same kinds of mass extinctions. Some are huge, like the Permo-Triassic one, 250 million years ago, that killed 90% of the species, something like that. Remember, the KT was only 60 or something like that. But some of them are only 10%. They are the minor mass extinction. Now, you must realize a minor mass extinction is worse than anything we could think of. But why are some very small and some very large? And some of our current research that will be shown here with the methane and the late Paleocene thermal maximum, with the Permo-Triassic coal and sulfur-bearing sediments. We've work being done in the Karoo in South Africa, which is a huge flood basalt with a very small mass extinction. We're now trying to go to the next generation, which is to see, after we think we've figured out the first order model, which is mass extinctions are mainly due to large igneous province eruptions, why are they different? Which are the parameters? And that will be the next generation of research, I guess.
Right.
Dagmar Rödig for the German radio station Deutschlandfunk. I would like to ask if you could tell us a bit more about the Quellwasser event in the Devonian.
About the Quellwasser?
Yes, where the...
Well, I think it's quite complicated even. Some people claim that there was some impact linked to that extinction, but apparently from new data that a lot of people have now, it means that it means that impact just post-dating as the main extinction. And in fact, this is a twofold extinction, which is mainly linked to climatic change and the huge anoxia almost everywhere. And it means, I think we can ask to Vincent, but I'm almost sure that there is a coincidence by now with some volcanic province during the Devonian also.
Well, I'm not sure I should be talking about that, because we're not going to present these results at this conference, because this is really ongoing work, far from being finished. We are working with two geochronology labs, one in Orsay, France, with Xavier Keller, one in Berkeley, US, with Paul Rennie, and Russian colleagues. We have collected samples from a province which is just to the east of the famous Siberian traps which you are studying, and which is called, it's got various names, we call it the Vilui province, where you have rifts and dikes. All the lava is gone because it's so old, it's been eroded, but the dikes and the feeding system is still there. We have collected rocks. We have now dated in the two labs, two samples, which is too small, and they're spanning the Famennian boundary. So we have a very strong hypothesis that there is a flood basalt just under the Siberian traps, to the side and to the east, 110 million years, something like that, older, which happens to have been more or less in the same place, and which might have been, this is why I'm saying the only missing one is the Ordovician, because with the Cambrian one that you heard about, and with possibly the Vilui ones, but they really need more work, we are just missing one.
I might just add one, not about this specific event, but to back up exactly as you say, that the general interest of these projects altogether is this very large connection between the large igneous provinces and the extinctions. And although the attention to the impacts is important, I think to stress what we're saying here, there are quite a number of extinctions which have no evidence for any impact of any kind anywhere near them, unlike the ones we've been hearing here. For example, Siberia, the Siberian flood basalts and the end Permian extinction, indeed 90% of species went extinct. This was, you could say it's close to the end of multicellular life for a little while. Although there have been little hints, really for the large part they've been discounted, and I will say that of the 60 rocks that we've analyzed so far, there is absolutely no iridium in any of them. So there's really no impact anywhere near that very largest of all mass extinctions.
Yeah, just add something about the Kalvasser event. This anoxia, it's a wider spread anoxia, is linked to increasing greenhouse effect. And here, if you're looking for clearly something, we have to look for volcanic province. There is no other way, because impact are really post-dating that. There's probably, and it's something quite complicated in terms of dating. But don't forget something also. I think we need extinction for evolution. Small and big. And I think this is important to see also this in a positive way.
Okay, so we're keeping and thinking of things that come back to our minds. You heard, I think it was in Gerta's talk, about this March 5th paper in Science by 41 authors claiming to show consensus that the problem of the KT boundary was solved, it was the impact and nothing bad. By this time, you've clearly understood that we do not share that view, but we go a little further. I'll be honest, I don't think I've seen such a bad paper in Science in a very, very long time. And 3 groups have immediately replied with long comments. These 3 comments have been accepted, and they will be published in the issue of Science, I'm told, either May 14 or May 21st. So since you like things that are, on time, I'm telling you that within 1 or 2 weeks, you should have 3 independent comments from 3 groups, one by Gerta, Thierry and their colleagues, one by my group, and one by a 3rd group of people that are all showing why this paper doesn't hold water.
That's interesting.
And those are only the 3 that got accepted.
Right. Science likes
Excuse
the
me,
impact.
no more comments about the paper in Science, please.
Sorry?
No more comments about the paper in Science. We keep it like this.
Is there competition?
Embargoed.
Are there any more questions from the journalists? All right, then I will end this press conference. And everyone, thank you for your time and attention.
Thank you.
Thank you all.